Hello and welcome. On behalf of the University of Cincinnati's Advanced Research Computing Center, my name is Matt, and this is the introduction to batch submission via SLURM on the high-performance computing cluster that we have here at the University of Cincinnati. This tutorial assumes that you have some basic introduction to Linux command line. If not, we have a tutorial video on that on the channel that you might want to first review. But if you are familiar, we'll go ahead and get started. So I'm already on the compute cluster, as you can tell via the hostname arc2. And I'm in this tutorial directory, which if I list the contents, you will see 4 files. The first 2 are just program files that we'll be messing with today. The contents don't matter, they're not important. And then these 2 .batch files, which are the SLURM submission files that we're going to be using. So if I look at the first one, which is just called submit.batch, you can see that it's roughly divided into about 2 parts. This first half in purple are all SLURM directives. They all begin with this #sbatch. And just going through them really quickly, these are basically requests to the scheduler to let the compute cluster know the resources that you need. And so this first line, partition equals public, this tells the partition to submit to. We're asking for 4 compute nodes, which correspond to 4 towers on our cluster. We have 64 tasks per node. That's the maximum number that we have available. You can request anywhere from 1 to 64 per node. We're asking for a maximum job time of 4 hours. After that, the job will be killed by the scheduler. And then the job name in this instance is just called test. There are many more directives that you can pass if you would like. There are thorough reviews online. We have a resource at our website, arc.uc.edu, if you'd like to review it for additional commands. But this is sufficient just for this tutorial. You'll see on the next 3 lines, these are all module load commands. So we're asking kind of the centralized resources to load our softwares. So in this case, we're loading the GNU compilers. We're loading OpenMPI because we're doing a parallel calculation. And we're loading LAMMPS, which if you're familiar with LAMMPS, you know that this is a molecular dynamics software. If not, don't worry about it. Just know that for this example, it's the software that we'll be using. And then this last line is the actual execution command, MPI run, to run in parallel. We're requesting 256 cores. This is the product of tasks per node and nodes, so 64 times 4 gives us a full 256. LMP is the name of the LAMMPS executable, and it's accepting this ar.in file as an input file. So before we submit, let's first check the status of the cluster via this sinfo command. So you can see here's this public partition that we're submitting to. We also have GPU partitions and a debug partition if you're interested in those. We'll cover GPU in a bit. But looking at public for a second, you can see that we have nodes in various states, drain, down, reserved. Some of them are already allocated. But for us, you can see on this line here, we have 49 idle, so we have plenty of room to submit our job, which we do via this sbatch command. And then the name of the submission file. And this will, when I hit enter, submit it to the queue. And you can see we get a message, submitted batch job 18698. So now if I want to see the status of that job, I can type sq. You'll notice that all of the SLURM commands from the command line start with an S, or most of them do. And so this gives me a list of all of the current jobs that are running on the cluster. And you can see ours is down here near the bottom. We called it test. That's my username. State R means that it's running, and it's been running for 17 seconds since the sq command was invoked. And we're using 4 cores, which correspond to compute nodes 28 through 31. If I want to filter this a little bit more, I can use sq with the -u flag, and then my username, and that shows only the jobs that I have submitted, so it filters it, and you can see that that's our new one, updated to 49 seconds. So while we wait for this job to finish, I'll go ahead and look at the other submission script that I have here, which is called submit-gpu.batch. And so the contents of this file, again, you can see that the upper half are all SLURM directives in purple. We again have some module load commands. In this case, we're loading some GPU drivers via CUDA and then an Anaconda environment. And then the command line commands are just activating this TensorFlow GPU environment. And then we're executing a script. Whoops. We're executing this script called gpuexample.py via Python. Actually, one more thing before I submit this. You'll notice that the commands or the SLURM directives that have changed, that now we have to submit to the GPU partition, of course, if we want to use a GPU node. And we also have to include this gres, which I think stands for greserve, and then one GPU node. So now if I submit this file again via the sbatch command, you'll see that we have the next job in line as well. And if we queue the scheduler, you can see that we have our old job is still running down here. It's been going for 2 minutes. And now this GPU test job has also been started on the GPU partition, and it's been running only for 5 seconds. This state is a useful thing to look at when your jobs are in the queue. Right now they're all running because we have resources available. But if you were waiting in the queue, this would say PD for pending, and the node list would give you a reason why you were pending, whether it would be for someone else is prioritized over you, or you're waiting for the amount of resources you requested, things of that nature. Let me again queue the scheduler to see where we are. And you can see that our GPU job has finished already. It was a very quick one. And then our CPU job is still ongoing on the 4 nodes. So let me look at the output of this really fast. You'll see we have a couple more files. Most of them aren't important. The 2 that I want to show you are these 2 slurm.out files. Since I did not specify a specific output name for my files, it just gives you slurm dash the number the job was .out. So 18699 was our GPU test, so let's look at that one using VI. And we can see that a bunch of stuff gets displayed from TensorFlow. The things that are most important for us, I just want to confirm that we're running. Yep, so whoops. On the GPUs, if I search correctly. Yeah, so here it is detecting them, GPU 0. And I've asked it to print that we have a GPU available, and of course we do. Otherwise we wouldn't have gotten submitted through the queue. And then this is the output of TensorFlow, which was just a simple matrix multiplication that we were doing, and it's running on the GPU. You can tell via this command here, executing operation matmul on device GPU 0. So just a quick little GPU example. Let me see how our other job is using. So now I've asked for jobs using my username, and now there are none left, which means that our other job has also finished. And I can look at that output. That's 18698. And this is a different program, so the output will look different, but I want to direct you. So we use 256 MPI tasks, and it took us a total of, at the bottom, wall time 4 minutes, 37 seconds. So you can imagine if you were doing this without a supercomputing resource, maybe just with 8 cores on your laptop or something, you know, this would be many times slower, and you would be waiting much longer for this result. So that's kind of the power, I guess, of the compute resources. You can submit your jobs in batch, and then they will wait in the queue and execute as soon as the resources become available. You do not have to be seated at your workstation for them to go, right? Once you've submitted them, they are totally fine. But maybe you don't want to submit to the batch queue. Maybe you want to run something interactively, maybe for debugging purposes or something. That's also an option. We can use this salloc command for that. I just want to go to the CPU partition because I know there are lots of idle nodes there. And using this salloc command, it tells me that it's granted me an allocation, and it tells me compute 15 is ready for my job. So I can simply use this SSH command to then transfer myself onto a compute node. You can see now that the host name has swapped from arc2, which is the login node, to compute 15, which is the 15th compute node. And so now any jobs that we execute here will be executed on that node. You can use all your standard Linux commands. You can see that the directories and folders and files are all of the same. And from here, if I wanted to like execute Python or something, I could do that. Whoops. Let me first load Anaconda. So I could load modules. Then I could load Python or run whatever interactive jobs I wanted to do. And when I'm finished submitting interactively, I can relinquish the compute node simply by typing exit. So connection to compute 15 closed. And then one more time relinquishes the job, so that way other users can use that resource. One more thing, I'm going to submit the same compute job one more time. Oops. Via sbatch. Let me check that it's there. And it is. It's been running. And now let's say this was maybe done in error, for example, and I want to delete this job from the queue because I don't want to burn compute hours if I know something is wrong. So I can do that, it's still running, via a command called scancel. And then I simply use the number of the job, which in this case is 18701. And then if I queue one more time, you can see that it's removing it from the queue via this state CG. And if I wait a little bit longer, it's gone entirely. And so that's kind of a tutorial for some of the basic SLURM commands. There are additional ones. Again, we have great resources at arc.uc.edu if you want to learn more. And I'll end this video just by a quick, very quick explanation. The way that the scheduler works in terms of queue prioritization, it prioritizes jobs based on the anticipated size, so how many nodes you request and for how long you request them, your priority if you're a priority user, and also how long you've been waiting in the queue. So it tries to, if you've been waiting a long time, accelerate you when you have resources available. This also means that you have to be careful in requesting your resources. The more you request, the longer you may have to wait for all of them to become available simultaneously for you. The scheduler won't schedule parts of your job while it waits for additional resources to become free. It's an all or nothing game. So do make sure that you submit what you need without being excessive. And so with that, that's basically it. You should be able now to submit some basic jobs, both on the compute and GPU resources that we have available. Look forward to seeing you in the next video. Until then, happy computing.